Good afternoon, everybody. My name is Mike Groves. I'm from a software company called Topolytics based in Edinburgh. And I'm doing this with Simon Dobson from St Andrews University. So we're doing a two Ronnies approach to the presentation. So it'll be context from me, and it'll be science from him. So if we kick off, what we're going to start with, I'm just going to take you back 25 years to a time in the 20th century when I spent 3 years looking at color infrared aerial photographs of the Black Forest in southern Germany. And you remember then, the UK was the dirty man of Europe. And we had this reputation for exporting our pollution and killing trees in Scandinavia and the rest of Europe. And this whole controversy around acid rain. So I spent 3 years looking at the health of trees in these aerial photographs because they weren't digital then. So I had to find somebody who had a drum scanner who could scan a transparency. I could then do some image processing and create what I grandly called crown conditioned surfaces, a way to sort of represent the health of the trees and the context in which those trees existed. So that their height, their species, the elevation, all sorts of different sort of contexts for that. And so that was great, and I then finished that, and I went to the job centre, and I said, they said, what would you like to do? And I said, I'd like to work in environmental management. And they kind of looked me in the eye, and they said, Sonny, I think you better go and get yourself a proper job. So I thought, okay, well, fine. Well, that's very good. Thank you very much. So I then ended up working in environmental management, and 25 years later, I still find myself working in environmental management. And this is what Topolytics is doing. So effectively, our trees are really industrial and commercial kind of waste, resource efficiency, water use, effluent. All of the things that Andy's alluded to. In fact, Andy's just set out a brilliant sort of commercial case for Topolytics, so thank you for that. So what we do is we allow a company to sort of contextualize all of these different data types. Now, the data, of course, could be from sensors, but it might not be from sensors. It might be literally from billing, or increasingly we're starting to get some data from drones, and starting to look at what useful data we can get from satellite imagery. But it's quite a complex mix, even for a small sort of manufacturer, a single-site manufacturer. You might have quite a complex mix of data on that site. But at the end of the day, what they need is something that's kind of really simple and really easy to understand and really easy to engage with, because we are in a context here where our customers, the environment and environmental management, on the one hand, it's a compliance pain. They've got to comply with SEPA requirements, etc. But on the other hand, they're starting to recognize, actually, there are cost implications here, not just in relation to compliance, but in relation to resource efficiency. So our big vision is to kind of effectively create a smart grid, but really for industrial and commercial waste and resource efficiency and emissions. But in order for us to get to that point, we've got to give companies, medium to large manufacturers and service businesses, something useful that they can use and something that goes beyond just keeping this information in an Excel spreadsheet, for example. So the whole user experience and the whole user interface is really important. Now, the approach that we've taken is to basically use geography. So this is going back to my early days. Is that actually, if you look at waste, look at movements of waste and storage of waste and generation of waste, geospatially, it's quite a complex picture. So if we can present that back to them in quite a kind of simple and engaging way, it's a way to get those companies actually populating the system. And one of the reasons that they populate the system is, number one, to get a better understanding of their environmental kind of risks and performance. But another reason, of course, is disclosure. Increasingly, they have to disclose this kind of information to third parties. Now, of course, it may be a compliance picture in relation to SEPA, or increasingly, it may be in relation to their customers. So there's a big element of supply chain pressure on companies here. So what we do is we make that process of reporting and disclosure much more real time, much easier, and hopefully a little bit more engaging than just basically filling out a questionnaire or producing a spreadsheet. And so it's that combination of data and insight on the one hand, but the ability to then project that and communicate that on the other. And this is an example of a well-known corporate based in Edinburgh. And effectively, we're presenting information on habitat, on waste, on water, on transport, presenting it, and they're presenting it back to their employees. It's an internal reporting mechanism. But we're also, again, coming back to this idea of, if you like, the smart grid, and coming back to the idea of the circular economy, being able to look at these metrics geospatially, we think is quite interesting and quite powerful. So even a single site could be generating quite a lot of different waste streams. So it's starting to kind of map where that waste goes. And then if you lay over other maps from other sites, you start to get some really kind of interesting opportunities around spatial analysis. So fundamentally, within this world of environmental sustainability, there is this great move from basic kind of data collection and compliance through to optimization and through to assurance and providing a level of assurance around the data. And that's one of the things that we're starting to look at in more detail. And that brings us on to the specific project that we've been working on with St Andrews. Because what people were saying to us, well, we've got data, we've got a real mix of data, but of course, increasingly, we've got data coming from sensors. So it could be meters, it could be air emission sensors. So we were part of a project, a small pilot at Grangemouth. There was a deployment of a small number of gas sensors, CO2, hydrogen sulfide, on a small part of the site run by Calichem with the help of Falkirk Council. And we were able to just work with that data and bring that data through an API into the system and start to play around with it. But one of the things that we're interested in is, what about the quality of that data? If we need to assure the kind of reporting that we're doing around this whole range of environmental risk and impact, then how do we do that with sensor data? So that was the purpose of the project, working with Simon Dobson at St Andrews. And I think Simon's going to then sort of talk more in detail about that now.
In the room drop when a graph went up on the slide. I mean, this, for those of you who are at the sharp end of dealing with data analytics, is what data quite often looks like coming in off a sensor. So we have 3 sensors here. They're all doing CO2. They're all nominally around the same sort of area. You'd reasonably expect them to be showing the same sorts of things. This is not what's happening. You can see all sorts of faults in here. There's this blue one that I would hazard a guess is doing its job properly. There's a black one which is doing its job okay, and then it kind of goes off piste a little bit and gets very much noisier, and then seems to go more quiet again. And then there's another one which really is swinging rather wildly and is swinging back and to between maximum and minimum values. So the problem that we ended up with when Mike came to us was, how do we deal with that and give something which is reasonably assurable and which can be presented to the guys who are running the plant in a way that they can make sense of. So this is the maths part. What you're dealing with in this sort of system is, what you're interested in is this process, which is a physical process that's emitting carbon dioxide. That's what you actually want to talk about. What you've actually got is a load of sensor observations, which are not the same thing, which have a whole load of noise and other things convolved on top of them to make things much more difficult. If you're in an environmental context, as soon as you put a sensor out in the environment, within a week something's growing on it. Plants around it grow and shield it. If you put it in water, then within about 3 minutes it's biofilmed. They deteriorate very, very rapidly. And those deteriorations are going to show up in the data, and you have no particularly good idea why, and exactly what is coming through as noise and what is actually real signal. So what we've added into Mike's dashboard is a system that will take a raw trace, this black trace under this diagram, and produce 2 things from it. It will produce a green line, which is where we think is the most probable reading, and it will also, which is rather different from other techniques, produce a confidence interval as to how confident we are that the real value is lying within that. And this is very, very adaptive. So it adapts to the fact that the sensor noise, the sensor behavior is changing very rapidly over time. So as this signal gets more noisy, this confidence interval will probably go wider and wider, and then it will come back together. If you have a situation where the real signal stops, the green line will keep going. It will attempt to do a best prediction of what's going on, but the confidence interval is going to get wider and wider and wider as we get less and less confidence in the value. So if you have a momentary lapse, you can make a reasonable prediction of what's happening, and then when the signal comes back, you can jump back in again. We can do this with multiple sensors. So for example, if you've got temperature and humidity sensing in the same environment, those two are very closely correlated. If the temperature sensor goes down, you can use the humidity sensor to fill in the gaps while you're waiting for everything to come back, assuming it does. Or if you lose something because of a communications dropout or any other sort of problem. We discovered that we could reconstruct. You can't really see it very well, I'm afraid, in this diagram. That we could use several techniques for reconstructing the signal. The real signal is actually just in here, and we have different reconstructions using different techniques. And the top two really aren't too bad. So we can manage the engineering issues that you get from sensors being deployed in the real world, and present them hopefully in a way which is easily understood by an operator or by a decision maker. There's an awful lot of mathematics running inside here, as you might imagine, all of which is hidden. It's all coming out as a most probable signal and a confidence interval. We're actually carrying on working with Topolytics because we're involved with Glasgow, Liverpool and Imperial with a rather larger grant than our initial case study that we did with Topolytics, and Topolytics are involved in this as well. It's a large EPSRC funded approach called the Science for Sensor Systems software that's intended to try and match up what the scientific or industrial mission of a sensor network is with exactly how you build the sensor network and how you would then perform the analysis. So we're quite excited to be able to carry on working with Topolytics and with these other guys on this.
Okay. And I think from our point of view, we're looking at a whole bunch of different ways that we can provide some level of confidence in the data that is fundamentally coming through our system. We're not taking the view that we just sit there, we're just a conduit, doesn't really matter what's happening at the other end. So we're trying to find a whole range of different approaches to this, and this was one of the things that we're doing there, but we're looking at other sort of predictive analytics approaches as well. So for us, this has been a great experience. So thank you to CENSIS for facilitating that. Thank you for Simon as well. And in the spirit of the two Ronnies, it's thank you from me.
And thank you from him.
Thank you.
Okay, bring the lights up and invite questions to the two Ronnies.
Who's Corbett?
Still can't see very well. There we go.
Hello, good morning. Very interesting. How do you determine between an event and an anomaly?
Okay, so you've hit the core question with this. All of these, when you draw one of these sensors, sorry, who am I talking to? Oh yeah, sorry, thank you. When you deploy any of these sensors, the only measurement you have about reality is what the sensors are telling you. So you don't have any what's called ground truth in the machine learning community. So these techniques are what is called unsupervised machine learning. You don't have a ground truth to compare against. So all you're doing is saying that from what we've seen in the past from multiple sensors, this is the most probable evolution of this signal. So that's good because it takes out a lot of noise and a lot of transients. What it will do is potentially slow down your ability to respond to an actual change. Now, it doesn't have to slow it down very much, but it's a little bit hard to quantify exactly how much it will slow it down by. If, for example, you have temperature sensing and something catches fire, the temperature will move very radically. You will initially throw that radical move away until it's sufficiently significant to bounce the signal. Now, how long that takes is very delicate to work out, and we need to improve it.
I mean, just on that, I mean, I think it isn't an exact science often, and therefore the approach that we're taking is about context. So you might have data coming from one particular type of sensor, but you've got data coming from other sources as well, and it's actually being able to sort of map those against each other that might then ultimately give you a better level of confidence in what you're actually looking at. So that's the kind of approach we're taking. It's like a geographic information system approach, but specifically to environmental management.
Okay. Introduce yourself, please, when you...
Yeah, I'm Frank Turnbull from CENSIS. Why don't you have built-in redundancy in each sensor type, so that if one sensor goes down, a second sensor can pick up the story, and then you wouldn't have to do as much analytics?
That's true. What we've got is we've got multiple sensors looking at roughly the same phenomena, which is a similar sort of thing. And multiple different sensor modalities looking at the same phenomenon, rather than having multiple of the same kind inside the same unit. I mean, you do have issues when you've got even two sensors inside the same unit. They are going to age differently, and possibly they're going to their noise characteristics are going to be different. But obviously, it does add more sensing, and so you do have a better level of a better observational capability. Most of the kit that one would buy off the shelf only has one sensor in each modality built into it. That's not necessarily the case, but that seems to be the way it goes.
Okay. One more. There's a hand raised way at the top left there. Well, from my view.
Thank you. William Harvard from PCME. A really interesting talk about this data quality. One of my experience is that you get a lot of error from systematic issues around instruments or sensors where calibrations are incorrect or the wrong technique is being used. Is that built into your confidence interval metric? I think it's a really interesting metric you're developing, but I think interested about your view on systematic errors.
It isn't at the moment. So drift is very difficult to deal with because you're getting a consistent, high-quality, incorrect signal. And we're much better off with noisy, correct signals. So not all nonsense is created equal in that sense. You can do something with it if the different sensors drift at different rates. That does help. I've actually got a student looking at this at the moment to look at the maintenance records for the sensors as well and try and integrate when they were maintained, because that will give you something about, even if they weren't recalibrated, at least they were cleaned, and at least if they were faulty, they were replaced. So actually, the maintenance record may tell you a lot of what you need to know. Now, the problem with that is that the maintenance record database is probably around, but it's not going to be linked up with the operational database in the sensing. You can do that with this particular student is interested in data warehousing, and you can do it with that. But I think that is a really tricky problem. The drift is one we haven't cracked. I don't think anyone's cracked it.
Okay, one more quick one. If anybody's got one to... Oh, there you go. Down in the front of the rear section there.
Hi, I'm just curious as to why a corrected or normalized or smooth signal is any more useful than the raw data itself. So
I think to answer that, you have to think about what it's being used for. So one of the things it might be used for is to sound alarms in a control room. If you've ever been into an industrial control room, one of the problems is that there are alarms going off all the time, and the operators learn to ignore the ones that are often spurious. What we think we could do, and what we've been trying to do with this dashboard idea is, for example, to set the threshold based on whether the 90% confidence interval breaches the threshold, as opposed to whether one individual data point does, which means you're going to get the noise in the signal isn't going to start triggering problems for you. So I do think that's a better front-end experience, if you like. But it goes back to what the gentleman over here asked. What's the latency on actually detecting events? You're essentially suppressing alarms by doing that, and you have to be clear that you're doing that, and that that's the right thing to do.
And I think again, I mean, it's about contextualizing. If you've got a network of sensors, they might be measuring one or two things, but also you might have other inputs as well. So all we're trying to do is build up a greater level of confidence that if you have a network and you're starting to sort of see something failing, we might be able to obviously we've got the modeling, but we might be able to look at other data inputs. For example, there may be an issue with odor and it's been caused by a tanker that's sort of tanking sludge. Now, the sensor may be picking that up, but we can also then bring in the GPS plot from the truck. And so we've got another level of context that we can add to that. So what we're saying here is this isn't an alpha, this isn't like the answer to everything, but it's just, we think it's just another way to just build a level of confidence in terms of the information and another level of context for what we're presenting. And again, the use cases will be different. So for waste, there is some sensing of waste, and obviously you can track movements of waste, and there is increasingly sensing around sort of containers of waste. But the sensor inputs are all going to be very, very, very different. So one of the things we're also interested to do is apply this to other types of sensor data, whether it be related to water level, water quality, waste, for example. But it will all be contextualized against other data inputs, whether they be from UAVs or from manual sources as well.
Okay, I think we should move on and thank the speakers. Thank you very much.
Well done.